Alright, thanks for watching. And today I would like to present you the 8th way of calculating the Gaussian integral. So congrats if you're still watching. I'm very impressed. And today we want to do the original way of calculating the Gaussian integral, the one sort of the first way that historically it was proved. So it turns out the polar coordinates method, even though it seems the most natural way, is not the first way. And interestingly, you would think that Gauss would come up with this first solution, but turns out no. Turns out it's Laplace who came up with this solution. So it should be called the Laplacian integral, but I think it's okay. There are lots of things named after Laplace. Alright, and it turns out that the integral Laplace was dealing with doesn't really look like the Gaussian integral at all. So consider now the following integral. I equals to the integral from 0 to 1 of 1 over square root of minus ln of x dx. You may say, whoa, this doesn't look at all like the Gaussian integral, but I'm claiming that yes, turns out it's a hidden Gaussian integral because it turns out you can make the following u-substitution. Let u be square root of minus ln of x. Then, what does that mean for x? Well, then it turns out minus ln of x equals to u squared. And then, if you divide by minus 1 and exponentiate, you indeed get x equals to e to the negative u squared. And we'll need this in a second. And then next thing, we need to do, the u substitution. So we need to calculate du. So du is just, by the Chen-Lu, 1 over 2 square root of minus ln of x. And then times minus 1 over x dx. Because you also need to differentiate this minus ln of x. Which tells us that we can simplify this a bit more. So 1 over 2. Well, square root of minus ln of x is u. Because in the end, we want to write everything in terms of u. So 1 over 2u. And then x is e to the negative u squared. So minus 1 over x is e to the u squared. Or because of this minus e to the u squared dx. But we don't really care about du. What we care about, we want to rewrite this dx. So in the end, dx, let's see, becomes minus 2u e to the minus u squared du. Lastly, just the endpoints. Well, u of 1, so the upper endpoint, it's square root of minus ln of 1, and that's 0. So ln of 1 is 0, square root of 0 is 0, and u of 0, strictly speaking, it's an improper integral, so it's u of 0 plus, it's square root of minus ln of 0 plus, and ln of 0 plus is negative infinity, so minus ln of 0 plus is infinity. And therefore, after this u substitution, our integral just becomes, drum roll, integral from infinity to 0 of, let's see, we have this minus 2u e to the negative u squared du. And that comes from the dx. And now, 1 over square root of minus ln of x is just 1 over u. So, over u. And then, how nice is that? The u's cancel out. And notice, this is in the wrong order, but because of this minus, it becomes in the right order, and we get 2 times integral from 0 to infinity, e of negative u squared du. And just by symmetry, you see that this equals to integral of minus infinity to infinity, e of negative u squared du. Which is our Gaussian integral. So it turns out if you evaluate this integral, then you also get the Gaussian integral. Now, why is this important? It's because we have a very important fact, which I will not prove because I don't know the proof of this, but it's a very nice fact that says the following. How cool is that? This video brings together lots of important mathematicians. Gauss, Laplace, and now Euler. Woo. What more you want? Like the giants of math come together. And what does Euler's formula say? It says the following. The integral from 0 to 1 x to the r over square root of 1 minus x to the 2s dx times the integral from 0 to 1 x to the r plus s over square root of 1 minus x to the 2s dx. If you multiply those two monstrous integrals, then you actually get a nice formula, 1 over s times r plus 1 times pi over 2. How cool is that? So it turns out, those two integrals might be pretty crazy, but if you multiply them, they're nice. Alright, and I know, this looks like just I pulled it out of my hat. But if you watch the whole video, at the end I'll explain you that, it's not as crazy as it seems. Because it turns out it's related to a previous video I made. But more on that later. Now, how can we use now Euler's identity to prove our fact? Well, let's play with this a bit. So, spielen wir damit. So, what can I erase? Well, I need this Euler's identity, so let me write this here. Because first of all, it's kind of interesting. There's a nice analysis, inside here, because we would like ideally to let r go to 0 and s go to 0. And you'll see why in a second, but it turns out the order matters. So first, let r go to 0. It's like this movie Argo, but here r goes to 0. Ooh. Okay, if r goes to 0, assume everything is nicely behaved and you can pass to the limit under the integral. So probably a dominated convergence thing in there. So then we get integral from 0 to 1 of x to the 0, so 1 over square root of 1 minus x to the 2s dx times integral from 0 to 1 x to the s over square root of 1 minus x to the 2s dx equals to 1 over s times pi over 2. So that's already very good. And now, we don't need the equality with r anymore. And now we would like s go to 0. And so one thing though, if I did it rigorously, the video would be like 2 hours long. So let me just do a little bit of hand waving. So let me put my applied math hat here a bit. So now we want to let s go to 0. First of all, it turns out this x to the s doesn't really matter. It's literally excess, too much excess quantity. Okay, so as s goes to 0, xs, well, it goes to 1. And again, let's ignore the fact that we're integrating from 0. Just for every positive x, pointwise, as s goes to 0, x to the s goes to 1. It's probably the pure math god being mad at me. Good. So as s goes to 0, x to the s goes to 1. And now notice the following. I'm claiming that the following holds. I'm claiming that 1 over x to the 2s is actually equivalent to minus 2s ln of x as s goes to 0. Why is this claim important? Because it helps us to go from Euler's identity back to our original integral, because here's where ln's appear. And well, let me quickly prove the claim. So why? It's actually a nice thing. So this squiggle just means that the ratio goes to 1 as s goes to 0. So let's just do limit s goes to 0 of 1 minus x to the 2s over minus 2s ln of x. Now, we want to use L'Hopital's rule, but careful, because we're taking limit as s goes to 0, we have to use L'Hopital's rule on s. So we're differentiating with respect to s, and for this, let's just rewrite the numerator, just to be clear. 1 minus e to the 2s ln of x over minus 2s ln of x. Now let's use L'Hopital's rule, but again on s. So this is limit s goes to 0 of. So again, use the Chen-Lu. So this one disappears, and then we get e to the 2s ln of x times 2 ln of x. So in other words, minus 2 ln of x e to the 2s ln of x divided by, now we're just differentiating with respect to s, and we get minus 2 ln of x. And lo and behold, those terms, they cancel out, and if you let s goes to 0, this just gives you e to the 0, which is just 1. So that's just e to the 0, which is 1. Or if you don't, if it's limit s goes to 0, x to the 2s, that's also 1. So indeed, this is true. 1 minus x to the 2s is equivalent to minus 2s ln of x. And now let's plug this into this identity. Again, the numerator I'm claiming is just goes to 1. So indeed, this just becomes integral from 0 to 1 of the same quantity squared. So at the end, what do we get? We get the following. I know, drama. It's like, ooh, what's gonna happen? Well, 1 second. So we get, if you plug this with Euler, and you let s go to 0, then we get integral from 0 to 1. Again, technically, 1 minus square root of x, 1 minus x to the 2s, but we've shown that it's equivalent to minus 2s ln of x. So in the end, we get 1 over square root of minus 2s ln of x dx times the same thing, because remember, x to the s, we just said it goes to 1. So we get this. So integral from 0 to 1, 1 over 1 minus 2s ln of x dx equals to, again, what did Euler's identity say? 1 over s pi over 2. But the nice thing is, notice there's this factor here that comes out. Namely, there's this factor of square root of, I think, 2s. So, again, first of all, it does become a square. 1 over square root of minus 2s, or maybe let me write that down as follows, of square root of 2s, square root of minus ln of x dx squared is, I guess, equal to 1 over s pi over 2 as s goes to 0. So strictly speaking, I don't mean exactly equal because, because of asymptotics, but I really just mean they're equivalent. So as s goes to 0, those two things are equivalent. And again, here comes a nice thing. This square root of 2s does not depend on x, so you can actually just pull it outside of the integral. So we then get as the following. We then get 1 over 2s, integral from 0 to 1 over square root of minus ln of x dx squared is equivalent to 1 over 2s pi as s goes to 0. And here comes the beautiful thing of, maybe the climax of this video. The 1 over 2s's, they cancel out. So what you get then is this constant is asymptotically equivalent to this pi constant, and therefore, because they're just constants, they have to be equal. And therefore, what do we get? Integral from 0 to 1 of 1 over square root of minus ln of x dx squared is actually equal to pi. And remember, this was an integral we really cared about. So I squared equals to pi, and therefore I equals to square root of pi. So in other words, our Gaussian integral, again, is equal to square root of pi. So how weird is that? I have no idea why this was the obvious way of coming up with this formula. I don't know, maybe Laplace just hung out with Euler, and Euler was like, I have this nice identity. I don't know why Euler sounds Italian, but I can't do the Swiss accent. But he was like, I have this nice identity. And he's like, we can actually use this to show our Gaussian integral. All right. So this, if you want, this is the end of the video, but if you still want to hang out with me for a couple of more minutes, let me give you the appendix. Namely, let me show you that this Euler's identity isn't something out of the world. So, remember what Euler's identity says. It said, so just a little remark. Euler's identity just says the integral from 0 to 1 of x to the r over square root of 1 minus x to the 2s dx times integral from 0 to 1 of x to the r plus s over square root of 1 minus x to the 2s dx equals to 1 over s times r plus 1 pi over 2. Okay. Again, scary integrals, we have no idea where they come from. Let me show you where it comes from. Because, so those are our two identities, A and B. It turns out you can transform those into integrals that are more familiar. And so consider the following substitution. Let x to the s be cosine of theta. So here, our u is cosine of theta. So in other words, assume everything is positive and we take the principal root. X is cosine of theta to the 1 over s. And then the usual dx is, again, use the Chen-Lu, 1 over s, cosine of theta of, I think, let's see, 1 over s minus 1, and then minus sine of theta d theta. So that's our dx, and then, what becomes at 0? So when is cosine of theta 0? It's at pi over 2. When is cosine of theta 1? It's at 0. So in other words, A can be just transformed into integral from pi over 2 to 0 of. So x to the r is cosine of theta to the r over s. And then, what is 1 minus x to the 2s, it's square root of 1 minus cosine squared, which becomes sine of theta. And then we have our dx, which becomes 1 over s cosine of theta, 1 over s minus 1, which you can write as 1 minus s over s, and then minus sine of theta, d theta. And lo and behold, the sine terms cancel out, and also this minus sort of rectifies this integral, and you're left with 1 over s integral from 0 to pi over 2 cosine of theta of, let's say, r plus 1 over s minus 1 d theta. So it turns out this integral A is just the integral of a power of cosine, which also brings us back to the seventh way of doing the Gaussian integral using the Wallis way, which involves powers of cosine. And similarly, you can also do it for B. So if you use the same u-sub for B, you get that B is 1 over s, integral from 0 to pi over 2, cosine of theta to the r plus 1 over s d theta. Okay, and so what does that mean? Let's plug in those two things at the same time. So in the end, what we get is, maybe let me do it here. So recall, we defined our quantity in to be integral from 0 to pi over 2 cosine to the n of theta d theta. And that was video number 7. The Wallis way of doing it. Then, what does Euler become? Euler is then equivalent to the following. Notice we have a factor of 1 over s and a factor of 1 over s. So 1 over s squared. And then I alpha plus 1 equals to 1 over s times r plus 1 pi over 2, where alpha is r plus 1 over s minus 1. Because all I'm saying is we get the factor of 1 over s here and 1 over s here, and then notice this exponent is just 1 more than this exponent. So it just equals to, powers of cosine times powers of cosine equals to that. And then we can just write this as follows. Then I alpha times I alpha plus 1 equals to s over r plus 1 pi over 2. But using this definition, this is just the same thing as I alpha times I alpha plus 1 equals to 1 over alpha plus 1 pi over 2. So Euler's identity is equivalent to this one, and I'm telling you, we've almost done the same thing in the previous video, because in the previous video, what we've shown is that I to n times I to n plus 1 equals to 1 over 2n plus 1 pi over 2. Notice how similar the two are. In other words, if alpha is an even integer, then we have shown Euler's identity. But Euler's identity is just a generalization for the case where alpha is any real number, maybe positive or something like that. Alright, so I hope you enjoyed this hipster way of doing the Gaussian integral. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.